All right, so it's an important release for metaprogramming. I thought we'll look at the past of metaprogramming, how we got to C++26, and then, time permitting, well, even though I'm being threatened here, we'll go also to the future of where we go from here. All right, so I want to go back to a story starting in 1994. Originally, my talk was going to go even back further, but I don't have time. So we're going to start with 1994, which is an important year for templates. Templates were first implemented in 1991, at least released in 1991. So after 3 years, people are starting to experiment. And 1994 is actually the year that template metaprogramming is invented in pieces. So the first one is that Erwin Unruh showed that you could do recursive instantiation and use it as a computational engine. Nathan Myers, who still sometimes attends these meetings, he proposed traits, right? And he used it for the standard template library at the time to configure strings and IO streams. But it became a very important technique for metaprogramming. Then Todd Waldhuizen and myself, we came up with expression templates in 1994. It wasn't called that yet, but it got that name a little later. Whereas Nathan actually invented the traits name right then and there. And that was an important part for template metaprogramming. 1994 is also a really important year for templates because of this little detail in the language, right? The standard template library was integrated in standard in that year. So 1994, key year for templates. And after that, nothing happens for years on the templates front, at least from what programmers see, right? We get the standard in 1998, and we haven't really made progress in terms of template metaprogramming. In fact, in 1998, relatively few people knew about all these techniques that had been found in 1994. Right, so we get our first standard. It doesn't say much about template metaprogramming. It doesn't really assume that there is any template metaprogramming. And then we get the next standard 13 years later. Now that's a very different standard from the first one. And in part because of metaprogramming. I think perhaps the most important event is that Andre published his book, Modern C++ Design. How many of you have read this book? Yeah, it's a very, very influential book, right? It showed that you could actually use these tricks for more than just tricks. You could use it for actual software engineering. So that was really important, and that's kicked off people using it everywhere. Nico and I, Nico is here also, by the way. I think he's here. Nico is here. We published a book that explained how to use templates and defined Sphene. So if you ever use the word Sphene, that comes out of that book. Gabby Dasrace started work the next year on something that will eventually become constexpr. Right, so again, constexpr becomes an important element in compile time evaluation, and in our later picture is going to be essential for metaprogramming. Doug Greger invents the next year, he introduces variadic templates. Right, another key element to template metaprogramming in this case. Stud enable if existed, was invented in 2003, but became part of the standard in 2007, introduced by Benjamin Koznick, but other people had invented the technique before, around 2003. And then Sphene, the original Sphene was not all that capable. It was just, you could substitute some types without triggering an instantiation error. But Steve Adamczyk and John Spicer wrote a paper that made it what we know today, and is actually also the basis for C++20 concepts in terms of what works and doesn't work. Now you see there's a gap there, right? That's because I want to talk about something else. In 2003, I made a presentation to the committee. And actually, just before that, the week before, there was an ACCU meeting. So I first presented at the ACCU, then at the committee. And it was a project of mine that I called the Metacode extension. Right? And it was a whole presentation, but I still have the slides. And so I copied one of the slides here. Right? This is a slide that summarizes all that's in the Metacode proposal, which wasn't really a proposal. It was more like a personal project. Metacode functions, you would have functions that you can evaluate at compile time. Imagine that. You could assemble code and then inject it in your program. We still don't have that, but we're talking about it. You could have a standard metacode library, which I didn't know the word reflection back then, or at least I didn't know it very well. So I call it the metacode library instead of the reflection library. But that's what it was. It was a reflection library. And I thought it should live in a namespace called stud meta. For those of you who know C++26, the reflection library lives in stud : meta. So I was close. And then there was this thing called metacode blocks, where you can, in between your declarations, you can have a bit of program that manipulates those declarations. And we have that in C++26. It's just not called metacode, it's called const-eval blocks. We'll see all that in a bit. So 2003, we were really well on the way to have the stuff we want. Why didn't it make it? Well, naive me thought that nobody wants all that code in header files. Who wants header files that are tens of thousands of lines of code, right? Surely nobody does that in C++, because this was 23. We had 10,000 lines, but not 100,000 lines or 500,000 lines like we have today. So I started a new project called modules. So I did that the year after, and I worked on that for about a decade. The project I got help from Doug Greger, who took it over, started chairing the modules meetings. And then Doug went to work on Swift, and Gabby Dos Reis took over. And then Richard Smith got involved, Nathan Sidwell, a lot of people contributed. And so we ended up having modules in 2020. Right? But for a long time, I was no longer thinking about metacode. I just started thinking modules, modules, modules. So that's why you didn't get reflection for a long time. But the committee was not as lazy as I was. So C+11 is now full of template metaprogramming, right? We have enable if, we have all traits, we have type traits, and so on. So they spin up a group called SG7, originally chaired by Jeff and Chandler, I believe, and now by Hanka. And they published their first paper that calls for proposals. Right? It says, okay, we would like to solve these problems with reflection, come up with a proposal. And someone from Czech Republic, actually, I believe, Mateusz Čašlik, comes up with a very... Slovakia, so sorry. so sorry. So I've caused an international incident, but I can check that off my bucket list now. So he publishes a very comprehensive paper that really explores the problem thoroughly and is based on template metaprogramming. Now, I'm busy with modules during that time, so even though I was at these meetings, I apparently was not paying attention. So I have no idea that this is happening. So people are meeting and they're developing this idea, and it eventually becomes a technical specification. So it's not exactly like a standard, but like a candidate for standardization. And some of the elements is, as I mentioned, is template metaprogramming based. It introduces a reflection operator. In the original paper, it proposed a couple of syntaxes, including mirrored, and then x is not just a variable name, it can be some construct. Right? And then later the committee says, well, let's make it, instead of a beautiful keyword like mirrored, let's make it a nice keyword like reflexper, right? And it's based on template metaprogramming. So what it does, when you do template metaprogramming, the best thing to work with is types. So reflection actually produces an anonymous class type, and then you can look at the members to find things out about this class type, and then it has a lot of meta functions. Right? And I put meta functions in quotes here because in template metaprogramming, a function is really a template, right? It's a class template that maps one set of template arguments to something else. So it had all the features that we have in C++26 in terms of capabilities. So it's great, except I finally noticed in 2017 that this work is going on. And I don't like the fact it's template metaprogramming. So I write this short paper, P0598, that says, hey, this is great capabilities, we want this, but could we do it instead with these new things that we have called context per functions? Right? And the committee says, yeah, that's a good idea, at least a large number of people in the committee. And so I started a bigger project, P1240, that takes Mateusz's work and translates it to compile time evaluation. Now, I should also give credit, Mateusz started it, but he got help from David Sankel and Axel Nierman that contributed to moving that forward. Most of the great projects in C++ are team efforts. So for P1240, I managed to get Andrew Sutton, who had successfully moved concepts into the language on my team, as well as Wyatt Childers, who worked for Andrew, and Faisal Valley, who brought you generic lambdas, and also context per lambdas. This is probably going to happen a few times, unfortunately. All right, so we have this P1240 paper in early 2018, and we're looking at the next standard in 2020. And we're like, we're not going to make it. In 2 years, we cannot specify all this. So, but we get some help. Andrew Sutton starts a company called Log3, and he implements the whole paper in Clang. So we have proved that it works. And we also can experiment to find out and tweak things for what they want. And we're like, okay, we can't get everything in C+20, but we can already prepare to have the machinery for metaprogramming in the future. So C+20 becomes the release where we add context per allocation, const eval functions, because when you do reflection at compile time, you don't want to accidentally evaluate your functions at runtime. So we made a variation of context per, it's called const eval. And people like Herb Sutter took this P1240 implementation and extended it for meta classes, right? So we could have an idea of where will we go in the future. I think we will still see meta class in the future. I don't think Herb has abandoned that project, so it's something to look forward to. I think it's pretty exciting. We also realized we wanted a mechanism to replicate statements based on some reflection container. And we almost got that in C++20, and we missed it because Jens here, who is the chair of the core working group, thank you, Jens, found all kinds of mistakes in it because he's so picky. And so we, by hours, literally by hours, we didn't get in C++20. Right? So C++20 gets shipped here in Czech Republic, in Prague, in February of 2020. So we're ready, we're going to work on P1240 and we're going to get that in the next standard, except there's a little problem, right? You know about it, so the C+ committee was no longer able to meet in person, and also there was a bit of slowness. What's more, we had kind of decided to go with value-based reflection, but then the discussion got reopened. So the few meetings that we had, instead of making progress, we started debating, should we go with template metaprogramming or value-based reflection? And eventually we went back to value-based. But the net result of all this is that in C++23, we were no closer than C+20 to having reflection and reflective metaprogramming in C++. Right? And to make things worse, Andrew Sutton and Log3 shut down, and Andrew Sutton went to work on non-C++ stuff. So we lost a big resource there. So I was really sad. But I have other friends. I mean, Andrew is still my friend, but I have other friends, including Barry Revzin. I don't know how many of you know Barry, but I often call the C++23 release of C++ the Barry Revzin release, because I think about half of the features in there, both in core and library, were written by Barry. So he's a very productive person, very sharp. And so I talked to him and said, well, could you help me make reflection come through? And so he said, yeah, I'm coming on board. Wyatt stayed on board also because he came to join me at my company. And so we decided, well, P1240 is just too big. Let's reduce it to the minimum viable proposal, right? And so we wrote this paper, P2996. You see, 996 is a good suffix because Matoush also started with 3996. And so we made it a minimal paper, and we also put in the title, Reflection for C++26, right? Just to set down like a foot, nah, I want it now, darn it. And I noticed later papers started copying us on that. So it's a couple of people wanted like a relocation in C++26, but that didn't work for them. Yeah, so we brought that paper to the next meeting. It was well received. We were encouraged to pursue it. And at that meeting, there was someone who attended for the first time. His name was Dan, or he still is, Dan Katz. And Dan had a group inside Bloomberg where he worked at the time, reviewing reflection. So he came, he gave us some input, some corrections. And he said, I'd like to be part of this project. Now, I can tell you, if he hadn't done that, and if we hadn't said, oh, yes, please come, the more the merrier, there would be no reflection in C++26. Dan and Barry are machines. And they worked so hard, 13 revisions there. Dan had never touched a C++ compiler before that. He implemented it in Clang and kept the implementation up to date with every revision of the paper. So if you ever meet him, buy him his favorite drink, which I don't recall what it is. But anyway, we did land not only the base paper, which had already grown from the R0 paper. R0 was minimal, R13 was not minimal. We had added a bunch of fun stuff in there, including const-eval blocks. But other people worked on other stuff, and we actually got 7 papers. I mentioned 4 here for C++25. So 296 is the base core framework for reflection. 3096, we had dropped the ability to look at function signatures. And Walter Genovese and Adam Latch said, no, we need that so we can automatically generate bindings to Python and JavaScript and so on. Thanks to that paper, we are able to do that in C++26. 3394 is a paper that brings us annotations. And you'll find that when you write reflection code, often you don't want it to apply willy-nilly to all your declarations. You want to be able to sort of tag it to particular declarations or customize things. That paper brought that to you. And then remember that paper that missed C++20 by a few hours? That made it. And again, only because Dan Katz saw that paper and said, hey, this paper would be really convenient for us. Let me take it, implement it, and ship it in the standard. So he's kind of Superman. Anyway, that made me all very, very happy for C++26. We have reflection, hooray, and that's where we are today. It's implemented in GCC 16, which is released now. You have to use the -f reflection option. I encourage you to try it. And before I go on, let's look at one example. Okay. Now, Andreas Andrescu told me, stop showing the example where you translate an enumeration value to a string. Nobody needs that. It's dumb. It's not good. So I'm doing it the other way. Right? We'll turn a string into an enumeration. Let me put my little pointer here because now we have code on the screen. I assure you it's not going to be too much. So there is a new header, meta, that defines all kinds of APIs for exploring your program. They are all const-eval functions, so everything happens at compile time. I'm going to, for a given enum, say capital X with some enumerators, I'm introducing a function string to enum that for that given X, if you give it a string that corresponds to an enum, it'll return an optional with the value of X or Y, in this case Y. So this static assert should work, right? And if it doesn't match any, we'll return an empty optional. So how do we do that? I write my template here. If you were a good person, you'd write a requires clause on that and so on, but this is slideware, so I don't want to overwhelm it, right? I pass a name as a string view, and the first thing we notice here is that this new operator, people give it all kinds of names, but it's reflection operator. Not mountain, not cat ears, not cutie, well, whatever you want to call it, but it's a reflection operator. So it returns a value of type stud meta info, stud : meta info. And that's the compiler's understanding of that thing. The only way you can use that value is copying it and applying various meta functions on it. So if it's an enumerator, if it represents an enumerator, which it should do in this case, right? I'm passing an X, then you can apply the function enumerators off on it. And that will return a vector, which each element describing one of the enumerators. Enumerators are these constants inside an enum, right? In this case, it'll be a vector of 2. Now you wonder, well, what if I did if I cheated and I passed, like, I don't know, namespace stud in there? Right? Oh no, you can't do that. May int. Well, then it'll throw an exception, because we now have in C++26 exceptions at compile time. And since you don't catch it, because who would catch it, it'll give you a nice error. But anyway, we'll pass it an enumerator, so it will work. We'll have a vector of 2 ints. And now there's a subtlety, is I'm going to use template 4, which is going to replicate this statement for every E in enums. The problem is, for various subtle reasons that I can't go into today, that template 4 doesn't work on a vector, right? And so I need a const expr variable. You can't have const expr vectors today. We actually talked today in the committee about making that possible, so there is hope for C++29. But right now, for a lot of good reasons, you can't. So you can convert a vector, or any range really, into a static array using define static array, and it will give you a span to that array. So I'm doing that here. That allows me to do template 4 over the enums, and it's really a template, right? So it stamps out different copies of the body. It's not a loop. It actually repeats it. It's as if you repeat that code. So it's going to be having one for X and one for Y. There is a function identifier of that. Let's come back. Okay, there's a function identifier of that for a given entity gives you its name if it has one, right? So I check the name against that identifier. So the first stamping out will check name against X. The second one will test name against Y. And this weird notation here is called splicer. That's the opposite of this one. So if you have a construct with the reflection operator, you can turn it into a value. With a splicer, you can turn it back into the actual construct. So I return either the X or the Y for that. And that works. You can follow that QR code, and you'll land on Godbolt where this program is compiled successfully. So I just want to give you that as a little bit of a feel for the taste of it. What I want you to get from this is that it really looks very much like C++ code, right? It's not difficult to write this. There's no weird template tricks. It's a little bit of a template trick with a template 4, but mostly it's straightforward. I hope you feel that way. So we have all this now, and some more that I'm not going into today. So we have a very good story for reflection in C++26. And we added a few things for generation. Now, the reflection part is great. It has a plan for the future, it's consistent. It's not complete, but it's pretty good. The generation part is just a few things that's not complete and doesn't have a plan for the future. And we'll talk about that in a bit. Okay. Now, the reflection part currently gives you a way to look at declared entities, things like namespaces, variables, functions, data members, that sort of stuff. Right? And you can take them apart, like you can ask for a class what all these members are and so on. But there's still a few declared entities that it doesn't cover. So captures, right? If you have a lambda, and inside the lambda you take the reflection of something that potentially could be captured, you'll get an error. And I'm hoping that for C++29 we can solve that. Right? Overload sets. Well, unfortunately, overload sets don't work. Now, I had examples for all of this, but it turns out I don't have time to go all over that because I've been threatened. But for overload sets, I think I'll show you an example. So let's say I declare two functions f here, right? They're overloaded. If you try to take the reflection today in C++26, that's an error. The single function g, that's not a problem. I'm going to take its reflection here, and that's okay. So as long as you find only one function, that's valid. Right? So I'm hoping that in C++29 we can define the reflection of an overload set, and then you can splice it back, but it's still an overload set. So if I splice set, I can still call it with either 42 or 42.0, and it will resolve whatever you want. So that's one of the future directions that we're looking at. Now, I want to be able to do operations on that set. I want to be able to say, well, explode the set so it becomes a vector of individual things. Right? The things could be functions, function templates, and a few other things. Right? And maybe I can add another function to it. Now, usually we make overload sets by lookup, so they all have the same name. But now I don't have to. I can add a G to all my Fs, and then turn it back into an overload set, and then splice it. And now I have an overload set of 3 things, so I can call it with null pointer, which matches the third one better, so it returns 3. Right? And you can transport your overload sets. It's something people have been wanting to do. So I think that's something I'm hoping we will be able to bring to you a few years from now. Another one that doesn't work is using declarations, and there is a paper to make that work. I hope we just didn't have the time to bring that in to C++26. I hope we can solve that soon. Bigger category of things that we can't do right now is expressions. And Dan Katz, who I mentioned earlier, has been looking at that. It's a big problem in part because all compilers handle expressions differently, and we have to decide whether we'll, what will represent. Now, we actually know that we want this syntax, so reflection operator parentheses, and then an expression. But then the question is, well, what can you ask about it? Can you ask, is it an addition? Well, maybe. What if it's overloaded set operator plus? Is that still an addition? Does it become a function call at that point, or is that too early? So there's some design problems there. Also, if this auto n were instantiated for int, then this character 0 gets converted to int. Do you get to see that it's a conversion or not? Right. So that's the kind of complications that have caused us not to have the C++26. Will it be in C++29? It's a lot of work. C++32, maybe.
You want language for ISTs?
Yeah. Someone made a comment, I want a language for ASTs. Is that what it is? Yeah, so we'll see. We'll see if we standardize the ASTs. Statements, you cannot ask a function what its statements are. Now, I don't think that's difficult to do, except compilers currently are allowed to throw away the statements once it's done with a function. And if we were to allow this, they would not be allowed to do that anymore. That's possible, that's okay, but we'll have to look at it. And then templates, you can have the reflection of a template. You can even substitute it and do fun stuff with it, but you can't look inside and ask what it's made of. Right. And part of the reason is that in C++, templates are not semantically analyzed. They're parsed, but we don't really know what they mean. Andreas Andrescu has written a paper, P3420, where he works around that by decomposing the templates in grammatical pieces that you can then put back together to reassemble a different template from another template. It's pretty neat, but it's still in the research stage. All right, so that's the reflection. We know what we want, we have an idea of how it works, we have a general framework that works really well. Now, for generation, we added splicers, right, which is useful, it's needed, but it's very point-wise. It's not you won't generate a whole function with the splicers. You can generate one little thing. There's template 4, that's good. Of course, we already have templates, and so a lot of metaprogramming still uses templates. So you do a bunch of computation, and then you call substitute to create a template. And then there's a bunch of functions that do generation for a particular thing. We already looked at define static array. Remember, it creates a static array in your program based on a range that you compute. The other in this group are similar. I won't go into them. Then there is one that's more interesting, and it caused a lot of controversy. We had to fight to get that in the standard, but we did get it, and so we're pretty happy. So this is also C++26 reflection code. How many of you have looked at the implementation of tuple in the standard? Yeah, good amount. So if you haven't done that yet, first make sure you're in a safe place, and then look at it. It's instructive. It's not simple. It'll have like tricks with base classes, template metaprogramming, and so on. It's not short either. But with C++26, you can do it a little better, I think, and with better compile times. So you declare a struct that has no definition, and we're going to give its definition procedurally, meaning we'll call a function to give it its definition. Now, I'm not in a function, so I can't run code, right? So we have this thing called const-eval blocks, so I can say const-eval open brace, and now I can put some code in there that will be executed, right? So I'm going to call this function called define aggregate. I give it a reflection of this type that's not quite, it's incomplete, so it's either a union or a struct. And then you give it descriptions of data members. So define aggregate doesn't give you the capability of defining any class. It allows you to only define like a C-like struct or union, right? A simple class, only data members, right? And then the data members, you have to give it a couple of parameters. The first one is a type, right? And you pass a reflection of the type, so you don't have to instantiate things all the time. C++26, you can give things a name underscore, and that doesn't conflict. You can have like 7 data members all called underscore, and that's okay. So we'll call them underscore, and then you pack expand over TSs, so I'll have a data member for each type that I give. And so with just these couple of lines of code, I have this data structure for my tuple. Of course, I have to make it an actual data member. This just creates a type. So I make it a data member, and now data has all the members I want for my tuple in many fewer lines than std tuple requires. If you follow that QR code, you'll also see how things like the get function and tuple element and so on are implemented. But it's really not that complicated, right? So that's great. So we have this define aggregate function. Can we Can we do other things like that, right? To start with, why just data members? Could I have maybe a nested type alias, right? That shouldn't be too hard. I'll just say, well, give me a specification for a type alias. I'll tell you what name it has, and what type it's resolved to. We can make that work, not a problem. What about an enum spec? We actually talked about this in the committee today, or a variation of that. You could have a nested enumeration, right? And I don't know exactly what we'll put there, but we'll put something that makes it work. We absolutely can do that. Class spec, maybe define a type alias at any scope, define enum. That's actually the one we talked about today in committee. And so there is a proposal to allow you to generate an enumeration definition for scoped enumeration, and so on. Right. Well, darn it. We have looked at that. We've worked with that, and we've tried to make it work, and we can make some of it work, but unfortunately not all. Right? In particular, when it comes to functions and templates, things get complicated very, very quickly. And so we don't think that's the future. That doesn't mean we shouldn't pursue it. We still work on it. And we think some of these, like we think defining them is a great idea. It's useful, and you can have it in C+29 instead of having to wait several standards before we solve all the other problems. So I think we should do something there. But it's still generation in lowercase and a bit fuzzy. Can I move to the next slide here? There we go. Yeah, I want generation big, nice, and future-proof. And personally, I believe that the solution has to do with token sequences. So now I'm going to present something that I like, that some of us like, but also some people really don't like, because it's a little different. So here, yeah, just a sec. Yeah. Here I'm going to introduce a new construct. It's a reflection operator to a brace enclosed bit of code. But it's not actually code, it's just tokens at this point. So this has no meaning at this point. The compiler, when it sees this, it starts swallowing this without trying to interpret what it means. It just sticks it on the side. And then if you give it to a function like QInjection, remember a console block, the compiler will parse all this, and then it will evaluate the statements in it. So it will see, okay, well, if B, and let's assuming B is true, then it will execute QInjection. And injection will say, take these tokens, and the next time the parser gets to run again, because right now it's not the parser, it's the evaluator, right? It's a constant evaluator that evaluates this. But next time the parser runs, you can look at these tokens and take them as if it was part of my program. Right? So if it's true, we do that, we finish the execution of this statement, and then we get after this brace, and then we'll see these tokens. Using type equals the semicolon, we interpret that, and we have the enable if for the true case. If it was false, we didn't queue the injection, and then nothing happened, and it's an empty type. Right? That's implemented. You can follow the QR code. Let's look at one more example. This one is a little more complicated. A lot of people would like to have a transformation from a struct to a struct where all the members have been replaced by an array of their original type. Right? It's useful for high-performance programming, and we'll do that here. So again, I have a template. I'll pass it a struct type. I have a constant val black, so I'm going to iterate over all the non-static data members of that struct. Right? So now I'm having mem is one of those infos that represents the non-static data member. Right? And I'm going to QInject these tokens, so array of, but now I need to create a type in there that's different for every token sequence, right? So I have this backslash that says, okay, stop ignoring the meaning. I want you to briefly look at the meaning. And so it's going to parse this and say, oh, wait, type of mem, I know what the members of T are, I know what the current member is. I'll replace this whole thing by the splice of the actual type. And then once I'm done with the end of bracket, I'm back in just eating tokens, so comma, okay, and okay. And then I need to give it a name, and I'd like it to give the original name, so there's a backslash, but now you say that you want the ID, not the actual thing, just the ID. And so that works also. And so now I've QInjected, say if you had a T with 7 members, I've QInjected 7 declarations of stud array of the original type, comma, whatever n is. Right? And then once we run out of conceval, all that stuff gets parsed, and now you have your structure of array. Again, it's implemented here. If you follow the QR code, you'll see the syntax is slightly different because we're playing with the syntax. This is the one that I like best today, but when I implemented it, I had a different syntax. And the nice thing about it is it's very easy to program with. You work with this for a few hours, and you'll find that you can do all kinds of fantastic things. It's also fairly easy to debug. We have functions where you can just ask to print out to your console what would be injected. So you can actually see, the code that the compiler sees. If you get an error, it will give it, because it still has all the tokens, so if, say, I don't know, if I put a colon here, it will point to that colon and say, this colon here, I don't like it, right? If you have a syntax error. So I think that's all I want to say. I think this is future-proof because no matter what we will design in the future for the language, it still be C++ code. It still be a bunch of tokens that you have to write, and you just can generate those tokens now programmatically instead of only put them in your source code. All right. If you're interested in more of this, there's a bunch of talks, lots of talks. You can just search for C++26 reflection on YouTube or something, and you'll find good ones. I'll recommend these 4, some of which don't exist yet. In CPCon 2024, I presented token injection, annotations, and an introduction to reflection in general, with many more examples than here. Barry gave a really good talk in 2025 for C++26 reflection and how to apply it. It's very compelling. Last month, he gave a talk that shows his vision of token sequences. So Barry is also working with me on token sequences, but he has his own sort of sensibilities there, and he implemented it in Clang. So that's kind of cool. And then next week, there is a AQ on C, and then we'll be talking about some of the subtle effects of C++26 reflection, because portability is not guaranteed, and he's going to talk about how to make sure that your C++26 reflection code is portable. And that's what I had for you today. Thank you so much for listening to me, and good luck. Enjoy C++26.